Good evening, everyone.
Hi there. Hi,
There,
all.
there you are. There you are. So we got Gerald McKeegan here, and we've got John Curry, and you see the name Rick Taft in the corner here, but Rick is going to be kind of working silently in the background. He graciously volunteered his new Canon camera that's an astro camera, and he's also learning how to do camera operation for this program. So, there he is. I saw a ghost of Rick. There he is. Yeah.
He's all
So
red.
anyway, we're really happy to have Rick on board and expand our team here a little bit so that we have a little bit of resiliency if one of us can't make it. So thank you, Rick. So who are we and what are we doing here? So we are presenting the virtual telescope viewing for the Chabot Space and Science Center, and we're all here with Nellie, our 36-inch research reflecting telescope. And normally, Nellie is used for public programs on Friday and Saturday nights, and people line up to view through the telescope. Of course, because of COVID, the center is closed to the public still, and with any degree of luck, we'll be able to reopen sometime in the fall, hopefully November. For public visitation again. And we have a whole bunch of different ones. And you can go to the Chabot Space and Science Center website at chabotspace.org to see the selection of virtual programs that we put on every week. We, of course, are dependent on the community for our financial support as well. The center being closed, we don't have admissions, we don't have the same degree of rentals of the facility that we have in normal times. So we count on your donations to keep the, in our case, keep the lights off, right? To keep the lights on. So we appreciate your support. Note for those on Facebook that there's a donation button, and we would love to get some donations tonight from anybody who is able. We also want to thank Fremont Bank, who is a community supporter, and for their support of the virtual telescope program. And we also have some really exciting news about Chabot in general. And I'm going to turn. Yeah, that's a hint. That's a big hint. So Gerald's going to talk about the new relationship that the Chabot Space and Science Center is about to begin with NASA. So Gerald, why don't you talk about that for a bit?
All right. Well, those of you who live in the Bay Area are probably aware that NASA has a major research center in the South Bay, Ames Research Center. And the Chabot Space and Science Center and NASA Ames Research Center are partnering together. And in that partnership, NASA will be helping out Chabot with exhibits, programming, connecting with the community, and so on. And Chabot will act as a visitor center for NASA Ames Research Center. So it's going to be a very great relationship. A lot of new exhibits coming out of this, a lot of new programming coming out of this. And of course, a great opportunity to highlight what's going on in terms of research at NASA Ames Research Center. There's a lot of stuff that goes on there most people aren't even aware of. And so they're going to have a chance to highlight some of their research. And also, Chabot is going to have a chance to enjoy the benefits of that relationship in terms of exhibits and programming. So we are really looking forward to this. And as Richard said, we are going to reopen Chabot in November. And when we do that, we're going to have a grand opening that will include both Chabot and NASA. And I hope when that finally happens, you all will take an opportunity to come on up and join us here at Chabot Space and Science Center and the NASA Ames Research Center partner for the Bay Area. All right.
Great, thank you.
Yeah.
So we're going to be starting tonight with the moon, and I got to tell you a quick story, and then I'll be quiet and let you guys take a look. So I was getting calls last week, throughout the week, from people who wanted me to find someone to send them photographs of the first sliver moon. And I was trying to figure out, well, why are people asking me for this? And then somebody explained, oh, well, it's Ramadan. And we know to begin Ramadan when we can first
Right,
spot a sliver of the moon after the new moon.
right.
And I unfortunately couldn't find anybody who was photographing the moon that night, but I did find some great internet images and forwarded them on where I could. But that was my lunar experience for last week. And maybe for tonight, though, we got a little bit more than a
Yeah,
sliver to show you. So why
yeah,
don't
yeah.
we, Rick? Why don't you share your screen, and we can put it on the moon.
Yeah, tonight we have what's called a waxing crescent moon. So we are seeing the eastern side of the moon that is being lit right now by the sun. And what we're going to do is kind of do a little tour around here. So I'm going to move the camera, or the telescope rather, just to kind of get up to the northern part of the moon and talk about some of the things. And Rick, you're going to have to help me out here by pointing out some things. Rick, you see two craters kind of side by side right there. Okay, that's Atlas and Hercules. Atlas and Hercules. And up above Atlas and Hercules, to the a little bit up and to the right, you can see it's might be a little hard to see, but there is a crater there called Endymion. And then to the left of Atlas and Hercules, you see a large smooth area. And we're going to be talking about a lot of these smooth areas here. That's Mare Frigoris. And the mares, that's the Latin term for seas. These are big, huge areas that have filled with lava. About 4 billion years ago, 3.8 billion years ago, there were a lot of big impacts on the moon, and some of those impacts were strong enough to actually crack the crust all the way down to what was then a molten interior. The moon doesn't have a molten interior anymore, but at that point in time, it had a molten interior, and those cracks allowed lava to ooze up through the cracks and fill some of these impact basins. And so when you look at the moon with your naked eye and you see what looks like dark splotches on the moon, those are the mares. Those are these huge areas of lava flow that flowed into large impact basins. And when you look at it with a telescope, you see that those areas are very smooth, and we call them mares. So again, the two that you see side by side there, that's Atlas and Hercules. I'm going to move us down a little bit to some other features. Yeah, right here. And let's go this way. Can I zoom in here? Okay, so you see the border area, just like that, Rick. You see the border area between the light and the dark. We call that border the terminator. And the terminator is constantly changing. It's because of the orbit of the moon around the Earth. The moon's angle with the sun changes constantly, and that's what causes the phases of the moon. So the terminator is the boundary between the part of the moon that's lit by the sun and the part of the moon that's still in the dark. And right at the terminator, you see another large, smooth area. That's the Sea of Serenity. And there is what looks like a crater right next to it. Hang on a second here. That's, I believe that's the Poseidonius. Yes, Poseidonius is that crater there. And then way over to the right, you see a large smooth area, almost to the limb, way to the right, right in there. There you go. That's the Sea of Chryses, Mare Crisium. And then we're going to move down a little bit more. And we see another smooth area, again, close to the terminator. That's one that a lot of people are very familiar with, right near the terminator to your left and up a little bit. Right there, that whole big smooth area, that is the Sea of Tranquility, Mare Tranquillitatis. And that is where Apollo 11 landed in 1969. The landing site is actually just inside the dark area, just beyond the terminator. So we can't see it right now. And then moving on down, let's see, a couple of things I wanted to point out here.
I'd like to mention when Gerald is doing this, it looks almost like he's just moving the image around, but that's not the case. We're looking live and he's actually moving the telescope.
Yeah,
Unfortunately, it looks like we moved it right off the object.
Hang on, I get it back here.
I think Gerald, did you sit on the hand paddle there? Or
don't do anything.
Yeah. There we go. Whoop. There. Whoop.
Yeah.
Technical difficulties.
Stand by here.
You're looking into deep space now.
But why can't we see any stars? It must be a fake.
Yeah, right. Okay. Yeah. If you could go back to the full screen view, that would be better. There we go. Here we go. All right. We found the moon again.
Yay.
I knew it was up there someplace.
Okay, now I'm getting where I want to be here. Okay, so what I wanted to point out to you is you see a couple of craters. One of those craters has a rather high peak in the center. That is the crater called Theophilus. And the one that it's overlapping is called Cyrillus. The fact that Theophilus overlaps Cyrillus tells us that Theophilus is a newer crater. And one of the things about the Theophilus is that it's got that nice peak in the center, what we call a rebound peak. And the rebound peak happens primarily with larger craters. And what happens is an asteroid comes and it hits the surface of the moon, impacts so hard it actually compresses the ground directly under the impact point. And then when the impact is done, that compression is kind of released. The pressure is released a little bit, so the ground sort of bounces back up. At the same time, all this material was pushed out to the sides, forming the rim of the crater. And some of that material slumps back down almost immediately and kind of combines with the material popping back up from the center to produce what we call the rebound peak. So that peak is pretty typical. Again, it's mostly larger craters that get a rebound peak. Smaller craters just look like a bowl. So you see right next to it, you can see a small crater, and that is just a bowl-shaped crater. The smooth area just to the right of Theophilus is called the Sea of Nectar, Mare Nectaris. And let's see, we're going to go down a little bit farther here, and I'm going to try to slew correctly without messing up again.
We got a comment in there. Please keep both hands on the telescope.
Yeah.
Yeah, it is a little windy up here today.
At the 10 o'clock, 2 o'clock position.
Right.
Okay, so bear with me here for a second. Rick, if you would kind of focus down towards the bottom there, you see a kind of a small clustering of craters. Right. So there's two of them kind of side by side, kind of overlapping each other. Metius and Fabricius. I don't speak Latin very well. So those two craters are actually pretty big. Metius, the one on the left, is about 53 miles in diameter. Fabricius is about 47 miles in diameter. And then going even farther south here, there's a crater called Vlach, which is actually just a little bit out of the field of view here. And right near the terminator there, you see two craters sort of right next to each other. Down. Yeah.
8 o'clock. Go down to your 8 o'clock position.
Yeah, there you
right,
go. Yeah, right there.
that.
So one of these is called Vlach, and the other one is called Rosenberger. And Vlach is about 54 miles in diameter, and Rosenberger is about 58 miles in diameter. So that's your quickie tour of the moon. Now you're probably thinking, boy, he really knows his craters really well. And I have to confess that I'm cheating. All right. So I'm going to actually reveal my secret here. So Rick, I'm going to bump you off here for a second. And I'm going to share my screen. Actually, no, I'm not. Rick, if you can stop sharing.
There you go. Oop.
Yeah, so what I wanted to show you is this book right here. So this is called The 21st Century Atlas of the Moon. The author is Dr. Charles Wood, and it's a great little book for touring the moon. It's got lots of plates in it, and it's very well organized, so it's very easy to find different things, where things are on the moon in different locations. It's got a little map down at the bottom, tell you where you're looking and so forth, and gives you, the names and a little bit of information about the moon. It's a great little book, and the best part about it is Dr. Charles Wood was my advisor when I got my master's degree. So I helped him out a little bit by buying that book, and I want to recommend it if anybody wants to, get a telescope or even a small pair of binoculars and tour around the moon. Having a book like that to help you out really is very helpful.
Kramer wants to know, who is the author again? What's his name?
Charles Wood, W-O-O-D. His first name is Charles, and it's called The 21st Century Atlas of the Moon. Excellent. And you can get it on Amazon. I think it's around 20 or 25 bucks, something like that. Very handy. It's just a spiral bound kind of notebook kind of thing, but it's got some great plates, and it makes it really easy. Once you're looking at the moon, if you say, well, trying to figure out what it is I'm seeing, this is a good way to answer that question. All right. Okay, what do we want to do next?
Well, you had some interesting things on your list. We had a bunch of items that were possibilities for tonight.
Yeah.
It's going to be we should wait a little longer till we look at the Sombrero, I think. So I think we could maybe go to the Coma cluster and maybe try out some of the galaxies there, or even some of the globular clusters there.
There's a couple of requests out there too.
Really?
M65 and 66.
Well, there is a request for M51, and we do have a special thing to show you with related to M51. So maybe we should head over in that direction, look at it through Nellie, and then show people Jared's photo.
Yeah. All right.
What do you think?
I think so.
All right, let's do that.
So we're going to slew, if you go to live view, Rick, and share your screen. So what we're going to do is slew on over to Algeba, which is a double star in the constellation Leo. We're going to use that as a stopping point, so we'll make sure we got the telescope synchronized with the sky. So we should see a bright star pop into view here in just a second. And there it is. There it is. Not too far off. Oops. Yep.
There we go.
Good to have both hands on the telescope and turn the steering wheel the right way. So,
and the actual double star is showing up pretty well there too.
yeah. So this is called Algebra. It's a double star in the constellation Leo. A lot of the stars that you see with your naked eye at night are actually not single stars. They're actually double stars, what we call binary systems, two stars orbiting around each other. Sometimes they are what we call optical doubles. So they're not actually gravitationally bound to each other. They just happen to be in the same line of sight. And so, like I say, more than half the stars you see that look like a single star to your naked eye, they're actually double stars. All right. M51. Let's head over to M51. Okay, so we're going to play a little game here, I guess you could say. We're going to point this telescope at M51, and Richard or Rick, you're probably going to do something like a 20-second exposure at ISO 3000 or 3200 or something like that.
Yeah, let's see. So what you want to do is go out of live view and go to imaging. Yeah. Yeah, your duration can, bulb and then pick, 30 seconds to start with.
Yeah, do you want to use ISO 40,000? No, let's see what happens.
We'll see what happens. It's a different camera, so we're going to play with the variables a little bit.
Yeah. This camera that we're using is kind of a little bit wider field.
And should get rid of the bullseye.
Yeah, we're off slightly in our aim.
But not
and the square. Get rid of the square. There we go. Oh, not bad at all. So you can increase the exposure now to 10 seconds.
How long was that? Oh, really?
Yeah.
Oh, yeah.
Wow.
Yeah, we are off on the aim a little bit. It would be good to.
Yeah, I just adjusted it.
Oh, good.
So go ahead and do your next shot.
Yeah, we're working on it. Oh, there we go.
Yeah.
You can go a little farther if you want, Gerald.
Okay.
And then we're starting to see the streamers between the two.
Yeah.
So this is the Galaxy M51, and M51 is a spiral galaxy that is feeding on another smaller galaxy that's right next to it.
Yeah, live view doesn't work for this, so you want to go to just a regular snap image. There you go. Yeah.
Oh, okay. So we're going to show you just what happens when we're taking individual images from this telescope. And then we're going to share with you how amateur astronomers produce those really beautiful images that you often see of telescopes or of galaxies and nebulas and so on. I can already see that this camera is more sensitive than yours, Richard.
Yeah, well, that's the idea.
Yeah.
Yeah. And what you can do is play with the light curves a little bit to darken that background. So wherever those are. Where are the? Yes. Yeah, are you still? Yeah, you want to be in imaging mode actually for this stuff. Yeah, there you go.
What's causing the light blueness in the background?
Yeah, leave it at 1600 and then try to take a 30-second shot. Yeah. Oops.
So you may think this kind of fiddling around and shooting a bunch of images that don't look very good are indicative of us not knowing what we're doing or not being very good with it.
And you would be right.
But what we're going to show you in a few minutes, there's an amateur astronomer. His name is Garrett Wilson. And Jared often comes up here back in the good old days before COVID. He would often come up here during our Saturday night public viewing events, set up his own telescope out on our observatory deck, and he would hook a camera to it. He's got a pretty nice telescope, and he would hook a camera to it and sort of demonstrate the process of creating a really nice image of a galaxy or a nebula or something like that. It's not an easy process. It involves multiple steps. And I'm gonna.
Yeah, why don't you switch over to Jared's image and we'll calibrate ours for this type of shot, and while you're showing that.
Okay, well, I'll tell you what here. Let me open this up. Oh. So what I want to start with, I'll just show you an image. And I'm going to bump you off here. And
yeah, that's fine.
Yeah.
Oh yeah. So what you could do? So let me show you something. This. Oops. Let's go back to here.
Okay. So here is one of the images that Jared
actually
produced.
Gerald, you don't have your image showing. You have your you have a Explore window showing.
It should be showing the image now. If you're watching on Facebook, you probably are.
No, I'm on the.
Really?
I'm on Zoom. Yeah.
Okay, let me.
You're just showing an Explorer window with a bunch of files.
Well, why?
I don't know.
That's the $1 million question.
Yeah.
There we go. Yeah, so that's about what you can expect.
All right, well, bear with me here for a second. We'll try to get back to.
Yeah. All right.
We're having lots of trouble here tonight, folks. Okay, tell me.
Because the weather's so good.
How's that?
There we go. That's better.
All right. Okay. All right. Sorry about that. Okay. So this is the image that Jared produced. And I say produced because this is not, putting the camera on the telescope, pointing it and taking one shot. And there it is. And it looks beautiful just like this. This took hours and hours of work. And so while you're looking at that, I'm going to read to you Jared's description of the steps that he went through in order to produce this image. It was a total of 10 hours of data in 3-minute subframes, so 3-minute exposures. He ended up with about 200 subframes altogether, so 200 exposures of about 3 minutes each. He did it through different types of filters. About half of it was done through what's called an H-alpha filter. That's a filter that sees the wavelength of hydrogen, hot hydrogen or ionized hydrogen, produces a distinctive reddish color we call H-alpha. And he did that so he could get some pop in the star forming region. Then he did about 2.5 hours of what's called luminance. And luminance is a black and white image. It's just something that gives you a lot of detail, but no color. And then he did about an hour for each of the 3 primary colors, red, green, and blue. So shooting multiple frames in each of those colors under moderately good sky conditions. Now, some of these images he took from his home in Oakland, but Jared also owns a piece of property up near Lake Berryessa. And so some of these images were taken up there where he has much better sky conditions.
Yeah, and the important thing to realize about that is this isn't taken in just one evening, right? This is taken over many, many evenings throughout the time period that M51 is visible. And one of the cool things you're able to do with a computerized astrophotography rig is be able to go back to the exact spot you were photographing on previous nights using a technique called plate solving, which allows your camera to be positioned exactly within just a couple of pixels, exactly where it had been positioned on previous nights. So that way you can combine the data from many, many nights, many, many hours into a final photograph like this.
Okay, so after he has taken all these images, the H-alpha images, the luminance images, and the red and green and blue images, now he's got a huge number of images and he has to process them. And the first thing he has to do is calibrate these images. To calibrate, we do two different things, dark calibration and flat calibration. So if you take a camera, any digital SLR camera or a CCD camera, whatever, and you cover the front end so that you're just seeing black, and you take an image, take an exposure, even though you're looking, or it should be just black, it won't be black. It'll have little bright spots here and there, maybe a streak here and there, lots of little imperfections. So what astrophotographers do is they shoot what we call dark frames. And in this case, he may have shot several dozen dark frames. Then there's another technique to further eliminate some of the electronic noise in the system called bias frames. And then another technique, when you point the telescope, say, at a white background and take an image, you'll see that there's imperfections caused by dust or variations in the lenses. Different things can cause little dark blotches in the image. So by shooting what we call flat frames, that helps you get rid of all of that. So you take the dark frames and the bias frames and the flat frames and you apply them to your H-alpha and red and green and blue and your luminance images to do what we call calibration. Now his camera, he's got a very high resolution camera. Each image is about 60 megapixels. So the raw file works out to be about 125 megapixels. So he ends up with about 60 gigabytes of raw data. And then he's got to go through a process of registering them so that they all overlap correctly. And then he works with the images, tweaking it with Photoshop. There's another program called PixInsight that he uses. And when he's all done, when he finally has the finished product, he's created a whole bunch of intermediate images before he gets to the finished product. And in this case, he says he ended up with 1/4 terabyte of images stored on his computer just to get this beautiful image that you see of M51. So,
yeah, in the process, you end up creating a red image, a green image, a blue image, a luminance image, and what he mentioned was a hydrogen alpha image as well, which is the part that he took here in Oakland. And then each of those are combined and registered and the colors balanced, so you get the very appealing view of the galaxy that you see here.
So the upshot is it's a lot of work.
It is a lot of work.
Getting a really nice astrophotography image like this takes a lot of work. It takes good equipment, preferably good location, in order to see all the detail. just to kind of give you an idea, not only can you see all the detail in the galaxy itself, you see all the gas that's been spread out because these two galaxies are merging. And if you look carefully, you can see some other galaxies. There's one right there. I forget where the other one. I think he's got a wider field of view version of this, which shows some others. Hang on just a second.
What I find remarkable about this is just the number of stars in our own Milky Way that he got in this image. Just the density of stars. That at first, when I saw this image, I thought, God, it seems like maybe there's a lot of noise in here. And then I zoomed in and I realized that's not noise. Those are stars. And it was remarkable.
They're excellent star images too. They're perfectly round and
It's really well. That's nice. Because he's got a really nice mount, a really nice telescope. This is a telescope which is called an astrograph, which is a type of telescope that's optimized for astrophotography, and it gives you a very nice wide field of view. But this just gives you a sense of how much work goes into producing a really nice image of some of these deep sky objects versus what we do here, where we're just doing one-off shots here.
Yeah, what we do here is like taking a snapshot, right? Yeah, it's like
with a Polaroid camera.
With a Polaroid camera, exactly. It's not even the same. You can't even really talk about it in the same sentence as what Jared is doing.
Now Jared has offered to contribute a little bit more, so. Especially when we get into times where, it's foggy or something like that, we can't look through our telescope. We may invite Jared to kind of get online with us a little bit and talk a little bit more about some of the stuff that he does.
Some of the processing. Show us some examples. That would be great.
Yeah. Yep. So, all right. So how are we doing on
I lost that image, but somebody asked a question. What is the small vertical line on the bottom left, right under the gas cloud?
The small vertical line.
I'd have to go back to the image because I can't see that.
I don't see a vertical line.
Yeah, why don't you share your screen and let's we can show our Polaroid of the same galaxy. Yeah, there we go. That's actually not too bad. And so the Rick was explaining that the blue tint that we've got, he has a filter on his camera right now that that isn't necessarily always there, but it happens to be there tonight, and that's contributing to the blue, but at the same time it's subtracting out some of the light pollution from the city. So you actually can see a fair amount of detail of M51 just from this quick 30-second image, and even though we don't have a nice black background on it. Whoa.
Oh, yeah, he's cranking up the gain there.
Oh, that's what you're doing. Yeah.
Now, one of the things you notice is the image seems to have a round border. And even before he did this, you can see off of the corners the sort of the edge of the image. That's called vignetting. And you get that, there's different situations where you can get it. But in this case, because this is such a wide field of view camera, we're actually seeing right out to the limits of the image that's coming off the telescope. So that's what's causing that vignetting.
That's pretty typical, especially on a wide field camera.
Right.
Or a full frame camera, right?
Right.
But we can see a lot of detail here. You see the dust lane or star lane connecting the two galaxies, and you could see the dust clouds. That's probably zoomed in a little far right now. There we go. That's good. Yeah, and obviously the bright core of each of the two galaxies. So have we talked, Gerald? I was working with Rick. Did you talk about M51 in general? It's like it's a very unusual galaxy. Talking about the collision, or did
yes, I did. Yeah, I mentioned that.
Got it. Yeah. I was busy playing with the software, so I missed that. So great. All right, we can move on then.
All right. Well, I was thinking we would go to M3 now.
Yep. Globular
M,
cluster time.
M51 is a galaxy that you're looking at now. So if we can go back to live view, we'll go ahead and slew on over to M3. I don't know if you're going to see it with live view on that camera or not. All right, if you're in live view, it's not working. So you probably have to do a 20-second exposure.
Yeah, do it in, don't do it in the live view, do it in imaging. Yeah.
M3 is a globular cluster, by the
Oh,
way.
look, it looks just like M51.
Yeah, you can
Get
cut
that
that down
image
to
out of
like
there.
20 seconds or 10 seconds. Yeah, that's fine. And the ISO may be a little high, but
So while they're working on that, let me tell you
There you
about M3. M3 is what we call a globular star cluster. Globular star clusters they're like a ball of stars out in space. This one's about 30,000 light years away. And it is filled with probably 500,000 stars. And the stars in the cluster orbit around the center of the cluster. And then the cluster orbits around our galaxy. But it orbits in a region we call the halo of the galaxy. The halo, I just saw a note from Garrett Wilson. He thinks the vertical line that you're talking about is an edge-on galaxy called IC 4277. I'm not sure that was the one he was talking about, but maybe it was. Okay, so we see now M3, and M3, like I say, is a globular star cluster. It orbits in a region of the galaxy called the halo. So if you imagine you're outside of our Milky Way, the Milky Way galaxy, and you see it looks like a flat disk with spiral arms in the disk, and it has like a central bulge. And around it, you see this very faint diffuse region we call the halo. The halo is filled with very old stars and globular star clusters. There's about 150 globular star clusters out there. And these globular star clusters formed when the galaxy was first forming. So the stars in the clusters are very, very old, at least 10 billion years old, probably closer to 12 billion years old. These are the remnants of the formation process of the Milky Way galaxy, and we see them around other galaxies as well. So it's a common occurrence when galaxies form. They end up with these globular clusters out at the periphery, out in the halo of the galaxy. The stars are very old. So all of the stars that we see are low mass stars. When it first formed, there were stars of all masses, high mass stars, medium mass stars, and low mass stars. But high mass stars don't live very long. And so the high mass stars, because this thing is so old, they've all died away. And because it's out in the halo and doesn't pass through the dust lanes and the molecular clouds and so on that are in the main part of the galaxy, it doesn't have any new material to use to create new stars. So the only thing left in the cluster is all these smaller, lower mass stars, which are the stars that live for many billions of years. So even though there's a lot of stars and looks like they're very bright, they're all very old stars. Now, you notice that it's pretty dense at the center. The stars, as they orbit around the cluster, they orbit in highly elliptical orbits that take them way out towards the periphery of the cluster, and then they slide back in, get close to the center. They're moving very fast when they're near the center, and then they swing around, and then they go back out. So they just keep going over and over and over again in this highly elliptical orbit, in and out towards the center. And when they're all towards the center, of course, they are very close together. When they go out to the periphery, they're much farther apart. One of the things that can happen with stars that are going in and getting so close together in the center is they can sometimes bump into each other or get so close to each other that they strip the outer layers of gas. One star will strip the outer layer of gas off another star, or they will bump into each other and actually merge to form a high mass star. So what we see in globular star clusters, we will occasionally see bright bluish white stars. Now, a bluish white star would normally mean that you're looking at a high mass star. High mass stars burn much hotter than low mass stars, and so they have a bluish white color to them. So when astronomers were first looking, closely at the stars in globular star clusters, and they saw all these bluish white stars, they couldn't figure out how that could be, because the stars should all be old. But then when they realized it was because of these collisions and close interactions, that you were either exposing the hotter interior of a star, or you were causing two stars to merge to produce a high mass star, that was the process that was involved. So the term they gave to these bluish stars in globular star clusters, we call them blue stragglers. So they are, in fact, old. It's just that because of these interactions, they look nice and hot and are bluish white in color. All right. And again, there's about 150 of these globular star clusters orbiting around the Milky Way galaxy out in the halo region. And at different times of the year, we're in a position to see more or less. We're getting into sort of globular cluster season. As we get closer to the summer, there will be more and more globular star clusters up in the sky. And that's because of the angle of the Earth's orbit relative to the plane of the galactic disk, of the plane of the disk of the galaxy. And because of that, the angle of our orbit, sometimes we are in a position to see a lot more globular star clusters than at other times. All right.
So Gerald, since we're kind of jumping from one type of object to another, maybe are we able to see the owl, or does the roof block that?
You asked me that once before. I think we can see the Owl Nebula. Let me.
So that way we can show people a planetary nebula as well.
Yeah. Well, if we can't see that one, we can always see the
Ghost of Jupiter. Yeah.
Well, the Ghost of Jupiter or the Clownface Nebula.
Oh yeah, Clownface. That's right.
So
it looks like the owl ought to be very visible. It's not. Yeah, it's up pretty high.
Yeah. Okay. Well,
okay, good. Let's give it a shot.
We'll give it a shot and see what happens here.
That'll be a hoot.
Oh.
All right, here we go. Sliding back across the sky. Yeah, the owl is actually pretty high, so the dome wouldn't be in the way. No. Okay, so it's going to take a long exposure here to bring this out. This is called the Owl Nebula. It's a planetary nebula. It has nothing to do with planets, though. Planetary nebulae, back a long time ago, astronomers thought they were planets forming, but it turns out they are stars dying. Planetary nebula happens when a lower mass star, like our sun, reaches the end of its life. The star becomes what we call a red giant. And
Yeah.
the red giant,
Take
there you
a
go. I can see the eyes of the owl. The red giant begins to lose its outer layers of gas and dust, mostly gas, because as it gets big, as the star swells up, its gravitational hold on its outer layers gets weaker. And at the same time, you've got all this turbulence going on inside the star in the convection zone of the star that produces these strong winds. And those winds will then start blowing the outer layers of gas out into space. And this goes on for a couple 100,000 years. And eventually, you expose the inner part of the star, the hotter core of the star. And also, what's happening at the core is the fusion process, which is what drives the star. That's the source of the energy of the star. The fusion process eventually stops. So whatever is left of the star, it collapses into a very small object. So a star that maybe was once 1,000,000 miles in diameter, it shrinks down and becomes only about 10,000 miles in diameter. And by that time, it has lost more than half of its mass. And this small object we call a white dwarf. A white dwarf is very compact. It's very, very dense. It's composed of what we call degenerate matter. And so it's extremely dense, but it holds all the residual heat left over from the star in a very small space. So the white dwarf is extremely hot, and it takes a long time for it to lose its heat. It's so hot that it emits ultraviolet radiation. But the white dwarf is surrounded by all of that gas that it was expelling while it was still a red giant star. And that ultraviolet radiation goes out and it ionizes the gas and causes the gas to glow. And so what you see there is kind of a puffball of gas. That's the gas that was expelled by the star when it was still a red giant. And if you look very carefully, right at the center, you can just barely make out a little dot, and that is the white dwarf at the center of the Owl Nebula. You know, we're pulling a little color out of it.
Yeah, starting to.
So we often see color in these clouds.
You can see a little hydrogen around the outside.
Yeah, and around the outer edge, you see kind of a pink periphery. That's hydrogen. The cloud is actually mostly hydrogen all across it, right? But inside, deeper in the cloud, you have a special kind of oxygen. It's called doubly ionized oxygen. And when doubly ionized oxygen is hit by that ultraviolet radiation, it causes it to glow in a very, very bright kind of a greenish blue color. And so that's why the interior part of this object has that greenish blue color. But as you get farther away from the white dwarf, its ability to ionize that doubly ionized oxygen isn't so good, and then you see more of the red color coming from the hydrogen. So this is called a planetary nebula. It's actually the end stage of a star's life. This is how our sun will end its life about 6 billion years from now. And we see this all over the sky. There are dozens and dozens and dozens of planetary nebula out there, and some of them have some pretty interesting shapes to them. The gas doesn't always come off of the star as a nice uniform bubble of gas. In fact, most of the time it does not. It comes off of the poles in a greater amount than it does off the equator of the star. It comes off in bursts, so you don't see one bubble, you see a bubble with shock waves within it. There's different patterns to it, but they're often very symmetrical. So they're really interesting to photograph.
There's a
satellite going through your image.
Yeah, I was just going to mention that. It looks like we got a satellite on the right-hand side.
Yeah,
we also got
that's happening more and more these days.
Yeah, with all these small satellites that they're putting up for these internet networks, we're going to have more and more satellites popping up in our images as time goes by.
Gerald, I have a question about the white dwarf, I believe. Is the center of the star turning into iron? Actually, the center of the star is no longer fusing anything. So no, it's not really turning into iron.
And because this was a lower mass star, there is no opportunity to create iron. Iron is only created in high mass stars, and high mass stars that are near the end of their life. In fact, when the iron starts being produced, the end of its life is days away rather than years or millennia away.
So Kramer was asking, I'm sorry, it wasn't Kramer, it was Rob who was asking if they're stars and not planets, why are they called planetary nebula? Well, and I had answered this a few weeks back that there's a lot of misunderstandings that took place back in the the 1600s, 1700s, 1800s when these types of objects were first observed, and they're kind of quaint misunderstandings, and modern astronomers have stuck with the terminology because it's kind of a fun terminology. Nobody knew what these things were, but they knew they weren't stars because they appeared to be spherical or almost planet-like. When you look at a planetary nebula, you could easily confuse it with something like, Neptune or Jupiter, right? Because it's it's a larger area than a star, and it's round, and it's got a color that's kind of obvious. So it must be some kind of weird planet, right? And that's kind of where astronomers were. Yeah, that's where astronomers were coming from back in the 1700s. But they knew it was gaseous because it looked that way as well. So they called it planetary nebula, meaning a round ball of gas.
Yeah.
And because of that misnomer, it gives us something to talk about whenever we have to describe what it is.
And explain every time we talk about it. Why is it called a planetary nebula? Hey, Bob Schock reminded us of something here. When you look at the planetary nebula, you see a brighter star, a very faint star, but it's a little bit brighter, right at the center. And then below it, you see two other stars. Those other stars are not part of the nebula. They're probably background stars that are just shining through the diffuse gas of the nebula. So the brighter one that's right at the center, that is the white dwarf. All right.
Good point.
Oh, he's got a little laser pointer thingy. How did you do that?
That's a secret.
Yeah. He's gonna have to show me that later. Yeah. I've always wanted one of those, and I never found how to do it.
All right. Let's see. Where else do we want to go tonight?
We had a request for M109 earlier, and also M81. But whatever you'd like.
Gerald, before we do that, is the Sombrero positioned where we could see it yet?
Good question.
I think it might be because
I know that was one of the objects you've been wanting to look at for a while.
Yeah, we're gonna have to.
I don't want to miss that opportunity on a nice night like this.
Yeah, we're gonna have to go low. Yeah. So I'm gonna salute back to algebra. Get us synchronized. So if you can go back to live mode or live view again. Are you in live view? Oh, wait, there it is. Okay. All right.
What star did you go to, Gerald?
Algebra.
You might want, well, yeah, Algebra would be good. I was going to say Spica might be a little closer.
Well, you know, the last time we were at Algebra, we could see that there was 2 stars there.
Right.
So that tells us that our viewing conditions are getting worse. Yeah.
Wow.
Yeah. Before we could see 2 distinct stars. Now, let me see if I can fiddle
touch
up
up the focus a little bit.
Let me see what we can do here.
Yeah,
That didn't work.
Nope. That's a little better.
That's worse.
Yeah, that's about all you're gonna get.
Well, that ain't good.
Yeah.
Okay, so now we'll go to M104 and see if we can see the Sombrero Galaxy.
I almost said Sombrero Nebula.
Well, that's what they used to call it.
That's what they used to
at one
call
time
it.
it was probably called a nebula.
That's right. Well, you know, nobody knew what galaxies were either.
Right.
You know, they you know, the astronomers thought they were some sort of nebula, and there wasn't a distinction between other galaxies and the Milky Way yet.
Is the dome gonna get in the way?
Maybe.
No, it looks like you should be okay.
Okay, all right.
It's close.
All right, we're there.
All right, so I would do
Yeah, it wasn't until the 1920s that it was established that galaxies were actually outside of the Milky Way galaxy. There was a very strong opinion among astronomers that galaxies were actually part of the Milky Way galaxy, that they weren't separate galaxies. They were just objects within our own galaxy. So you're doing a 20-second exposure, right?
Well, at least to start with, yeah.
And the answer is,
there it is.
Hey, it's not too bad.
That's not bad at all.
Yeah, let me move west a little bit here. Okay, might want to try another one. So the Sombrero Galaxy it's a spiral galaxy, but it's a little bit more elliptical. It has a much more prominent halo around it, and we're seeing it almost edge on. And one of the cool things about that is you can really tell that within the disk of the galaxy, there is a lot of gas and dust. You'll see it here in a second when we get to the next image, that it actually obscures a lot of the stars within the galaxy.
Hey, this is a good question. How much does Nellie weigh? I mean, I guess we got to have to count with the mirror, right?
Yeah, it's
14,000 pounds.
Yeah, telescope and the mount are 14,000 pounds.
Right. And without the mirror, it's a lot lighter.
The telescope itself is about 2,000 of those pounds.
And
Right.
the primary mirror weighs 465 pounds. Okay.
Debbie says it's not polite to ask a lady your weight.
So even in this image, you can see the dark dust lane. And the bright core, the shape of this galaxy tells us that it has a very large black hole in it at its center. The bigger the central bulge is, the bigger the black hole at the center of that central bulge. So Sombrero Galaxy has pretty good size black hole in it.
Yeah, it takes up a good portion of the total galaxy, that central bulge.
You doing another exposure here?
Oh, wrong way.
Oh, that's odd.
Harold, you have the pad upside down again.
Okay, so that's weird because I've been moving it west, which should be the right
Yeah.
direction, but apparently we're flipped mirror image, which we don't do with Richard's camera. So,
You know, I noticed on M51 it looked like it was a flipped image. Is that possible that you were flipped the whole time?
well,
It could be that he, you know what? Rick has the flip setting. It is flipped.
Yeah.
oh man.
Yeah, the one next to it, Rick, is yeah, that's the one that was flipping it, I think. If you click it again.
Ah, yeah.
There you
Now I see what's going on.
Yeah, that's all right. You know, this is all a learning experience. It's what happens when you put the Polaroid film upside down. Yeah, it's
It
all
was
a test. It's
It
all
was
a test.
That was a
Yeah,
test.
it's all a test.
Well, it took me a while to pass
See
the
if Gerald
test.
is paying attention.
Yeah, see the left side of the screen now that everything's oriented correctly, the left side of the screen is east, the right side of the screen is west, and the top is north and the bottom is south.
Yeah, Rick, are you gonna want to take another shot?
Yeah, I hopefully you got it centered up a little bit better now.
No, you could probably take another one here and then adjust the. Yeah, I think the 45 is probably good. Once we get it more centered.
Yeah, we're starting to get close to running out of time, so.
Yeah, this will be. We'll just get this one centered, talk about it for a bit, and that'll do it.
You know, I wanted to end with one thing. We were looking at M51 earlier, and we saw that nice image that Jared produced, and the not so nice image that we produced in our one-shot deal here with this telescope. But NASA really recently came out with something that was just really cool. They decided to put music to M51. And so what they did is they took the image of M51 and they created a sweeping arm, and as it passed over the different intensities that you see in the image of M51, it would play a different musical tone. So
you could move this arm with your mouse or something?
No,
on
it's
the side or something?
all
Or?
automated. You just
You just watch.
No, if you moved it if you had to move the arm back and forth, then it would be the DJ version.
Okay, so one more time, huh?
One more time, a little bit more, and we'll take one more shot.
Okay, go ahead.
We all have OCD here and want it centered.
Yeah,
Yep.
must be centered.
Margot asks,
yeah.
how far away is the galaxy? And looks like it's about 28 million light years.
I was going to guess 25, so that's pretty good. Yeah.
And it's probably somewhere in between.
Yeah.
You know, our technique for measuring distances to galaxies is not real precise. So
it's in the ballpark.
Take any number we give you as a ballpark number.
So what that means is you're looking at the galaxy as it appeared 28 million years ago.
Yeah.
And those are old photons.
So somebody asked if we could
Fortunately-
create an image from multiple telescopes at different locations synced via the internet.
Nice.
Well, you can, but it's a lot of work to do that.
Yeah, that would be really tough to do.
Yeah, but it can be, and in fact, they do that sometimes using a technique called interferometry, where they have multiple telescopes, point them at the same thing, combine the images together. But it's a lot of work to do that.
Sure.
But the cool thing about doing that is if you have, say, 6 telescopes that are far apart from each other, and you point them all at the same object and image at the same time, and combine those images, the resulting resolution is exceptionally good. It's as if you have a telescope that says, wide is the distance between all these individual telescopes. So you get really good resolution doing that. But it is an extremely difficult process. Lots of image processing involved because you have to synchronize all the images, and because they're coming from different distances, there are slight differences in the time it takes for them to reach you, and you got to compensate for that. There's a lot.
And the image scale is different from telescope to telescope.
Right. So all of
Makes it
that has to
harder.
be taken into consideration.
That's pretty neat, Rick.
That's close enough to the center for me.
It's almost what it looks like in the daytime. It's got the blue sky. You might want to play with the light curve a little bit, see if you could.
Let's see.
Probably pull it down a little bit. Yeah, there we go. You get a little more contrast.
So do I see another question about how far away it is? It's 28 million light years away.
Yeah, that was Margot's question. Yeah,
Okay.
got that. All right.
All right. So if I can do my one last thing here that I've been
Of
wanting.
course.
Okay, so I'm going to share my screen here.
Oh, are you going to do the musical M51?
Yeah.
Uh-huh.
Musical M51 here. Let's see if I can get to it. All right, can you all see that?
Yeah?
Here we go. Can you hear it?
No.
No.
Oh, well, in that case,
You know, there might be a setting somewhere. where you have
yeah,
to-
I know what I did wrong. Here, hang on just a second. Okay, so I'm going to stop the share and restart it and click that little button that says
That's right.
share computer sound. All right. Okay, one more time. You hear it now?
Yeah. Excellent. Oh, I like that. As it goes by the brighter
Yeah.
stars, you get.
All right.
Oh, very good.
The
Gerald-
music of M51.
Gerald, are you going to make that your ringtone?
You're right.
All right. Well, I guess
Okay.
that wraps it up for tonight. I want to express my appreciation to Rick Taft for bringing his astronomy camera with him and helping out tonight. I only had to do the back end stuff, and it was a lot easier than managing 5 things at once. So appreciate it, Rick. Thanks for joining us.
Yes, you're quite
And
welcome. Yeah.
we'll be seeing more of you, I hope. And Gerald and John, have a good rest of the weekend, and we'll see you next week.
All right.